This conference will now be recorded.
Hi, my name is Mauricio Cespedes. I am a power systems engineer with Facebook, and it is my pleasure to present this talk entitled Development of System Specification for UPS. UPS here stands for Uninterruptible Power Supply, the type that is used in the data center and rated for several megawatts. This talk is the result of 2 years of research on the electrical system stability of the Facebook data center. And these results would not have been possible without the collaboration of our industry partners, Eaton, Schneider Electric, and Vertiv. I will add some more acknowledgements at the end of the talk, so let's dive right into it. These are actual current waveforms measured in a Facebook data center back in 2017. The currents were measured in a main switchboard, or MSB, rated for 3 megawatts. We observed in the current waveform that instead of having a good sinusoidal waveform with flat amplitude, there is a low frequency envelope that distorts the MSB currents. At the time, if you were to approach one of these MSBs while the current was oscillating like this, the sound emanating from the MSB was described to us as resembling a washing machine sound. This was clearly a risk to the data center operation, and it was a problem. The origin of this resonance was back in 2017, as I mentioned earlier. Here, the green trace is the total MSB load in kilowatts, and you see how as we were increasing the load, sometime in June 2017, the MSB neutral current started to spike. If you were to measure the MSB currents whenever one of these spikes was happening, you will see the waveform that I showed in the previous slide. To explain the resonance, we have successfully used system stability theory based on system impedances. This theory shows that interconnection of data center and rack power supply units, or PSUs, creates a feedback loop. In this diagram, on the data center on the left, it has a certain impedance, CS, and then the power supply unit is on the right, and it has an impedance labeled CL. When these two systems are interconnected, we can model the system with this simple electrical circuit, where CS is the building impedance or data center impedance, and CL is the load impedance or PSU impedance. And then the voltage on the PSU is a function of the ratio between the impedance of the source and the impedance of the load. If this impedance ratio were to become -1, the denominator becomes 0 and the voltage becomes infinite and the system is unstable. So the objective for system stability is to maintain this ratio away from -1. When would this ratio be -1? That will happen when the two impedances are equal in magnitude and when the phase difference between the source impedance and the load impedance is 180 degrees. So for a stable system, we want to prevent the impedance ratio from being -1. This can be done establishing a magnitude constraint, which says that we prevent impedances being equal when the phase is 180 degrees apart between these two impedances. We can also have a phase constraint that says that when impedances are equal, we prevent the phase difference from being 180 degrees. If we practice these two fundamental principles, then the impedance ratio should not be -1 and we should have a stable system. So going back to how this theory explains the resonance we observe in our data centers, here is a DFT of the waveform that I showed you earlier. In the DFT, we observe a large red trace at 60 Hertz. That's the positive sequence fundamental component with 100% the amplitude. There is a blue distortion at 71 Hertz. Blue here stands for zero sequence. And there is a coupled component at 49 Hertz with a negative sequence. If you're not familiar with sequence components, positive, negative, and zero sequence components are just a different reference frame to analyze three-phase systems, which makes it a little bit easier since most of the time sequence components are uncoupled from each other and allow us to analyze each sequence network one by one instead of analyzing a fully coupled 3-input, 3-output, 3-phase system. All right, so we have a zero sequence component at 71 Hertz that is causing the distortion. Let's see why that is. These are Nyquist plots of the impedance ratio. The blue one is for the zero sequence impedance ratio. The red is for the positive sequence impedance ratio, and the black is for the negative sequence impedance ratio. In Nyquist theory, the impedance ratio of the plot should stay away from the -1, 0 point here. That doesn't happen for the zero sequence plot. The positive sequence plot in red and black, the negative sequence, they both stay away from the -1, 0 point, but the zero sequence does not, and it actually goes around the critical point, which causes instability. So from this analysis, we conclude that the zero sequence impedance ratio shows or predicts instability. So this is a more detailed analysis of the zero sequence impedance ratio between the source and the load. The plot on the right shows in blue the load impedance that we can measure in the lab, and in pink is the data center impedance that we can also measure. The data center impedance is mostly inductive, represented here by this straight line. It's mostly inductive because it's mostly composed of cables and copper in the switchgear that represents the data center. We see that the impedance of the data center in pink intersects the load impedance of the power supply in blue at this frequency, which is close to 70 Hertz. So at that intersection, that means that the two impedances are equal. And now, since the phase difference is also 180 degrees at that intersection frequency, then we should have instability at 70 Hertz. So that's the frequency where the Nyquist plot leaves the unit circle. And then based on this zero sequence impedance ratio analysis, we predict that there will be instability at 70 Hertz, and that explains our waveform observation. Here is another instability case. This slide shows some high frequency distortion that we observe in a data center. These are some videos. So the one on the left shows the power supplies in a rack suffering from harmonic resonance. There is not much you can see there, but when we connect an oscilloscope to the power input of this rack, we obtain the voltages and currents on the video on the right. So in this video, you see that as the operating condition of the data center changes, the distortion in the waveform of the currents comes and goes. And then this is a high frequency distortion clearly, and from the DFT at the bottom, we see that it's mostly located around 7.4 kilohertz. So we took these waveforms and brought them into our computers and did some DFT analysis. So DFT analysis of these voltages actually confirms that most of the resonance is around 7.3 kilohertz. We did some detailed impedance analysis here as well. And for the impedance that we measured for this PSU, the intersection with the data center impedance can occur somewhere around 7 kilohertz. So that confirms that at this intersection frequency where the two impedances are equal, the phase is also close to 180 degrees. That's the phase difference. And so the impedance ratio predicts, again, system instability around 7 kilohertz, which confirms our observation in the waveforms. So to prevent these unstable interactions, we have imposed impedance constraints. We will show how these apply to the data center impedance. So at low frequencies, we focus on a magnitude constraint. The magnitude constraint aims at preventing an intersection in a frequency region where it is very hard to prevent a phase difference of 180 degrees. So for a data center, the magnitude constraint says that the impedance of the data center should not be anywhere inside this shaded region. That's a region allocated for the power supply impedance. If we keep them away in that frequency region, there should not be any problem. At high frequencies, we impose a phase constraint. The phase constraint aims at preventing a phase difference of 180 degrees in a frequency region where impedances are likely to intersect. So here the shaded region or forbidden region is above 85 and below minus 85. So the region between minus 85 and 85 is the allowable region. That's where we allow impedances to be located, the phase of the impedances. and this is a high frequency constraint. These are shown mathematically here. So on the left, the magnitude of the source impedance, which is the data center impedance, should be below a certain value, 1/2 of the nominal inductance of the system. Nominal inductance also is sometimes referred as rated or base inductance. And this is a constraint that applies for frequencies below the second harmonic. The high frequency constraint that we impose on the angle of the impedance is shown here. Basically, we have an allowable region between -85 and 85 degrees, and that constraint applies for all frequencies above the second harmonic. The new Facebook data center is required to comply with these new impedance specifications. To the left, there is a picture of the Facebook data center lineup, and to the right, there is a one-line diagram of the data center electrical system. So for every component in this system, from the input transformer or PTX to the switchgear, the cable, and all the interconnections down to the power supply, we have imposed impedance specifications for all of them. If there is an inline UPS, as shown here in the diagram in blue, they are also subject to impedance specifications. So at this OCP, we have 3 talks dealing with these impedance specifications. This one is dealing with UPS, or will deal with UPS. The next one is on the system in general, and there is another talk on power supplies. These schedules shown here are before the OCP went virtual. So this talk focuses on UPS. The UPS in a Facebook data center processes part of the power served to the network infrastructure. There is a section of the power in the data center that is not served by the UPS. So by model reduction techniques, we reduce the data center model to an equivalent circuit with only one UPS and a set of PSU loads, one that is fed from the UPS and another PSU that is not fed from the UPS. There are also some impedance interconnections labeled here as L0, L1, L2, and L3. The UPS has multiple operation modes depending on which components are operational. In this diagram, the UPS has a static bypass, a rectifier, an inverter, and a battery bank, which is interfaced by means of a DC to DC converter. Our impedance specification applies to all the bypass, the rectifier, and the inverter, and their different operation modes. For the bypass mode, the UPS is just a copper bar that connects the data center to the power supplies downstream. In double conversion mode, both the rectifier and the inverter process power to the PSU loads. In stored energy mode, both the inverter and the battery bank are involved. There is a mode called Inline Interactive with bypass. In this case, the inverter may or may not operate while the bypass is engaged. The bypass mode is perhaps the simplest one, and we'll start with that one. We'll see how we developed specifications for it. So by reducing the system model to just a couple of power supply units, a bypass impedance, and the rest of the interconnecting impedances, we can apply our impedance constraints to this system and determine the allowable bypass impedance that maintains stability. Based on our analysis, we determined that 20 microhenries per megawatt of UPS power is an acceptable bypass impedance. In these equations, LB is the bypass impedance, and it should be less than 20 over Pn, where Pn is the nominal power of the UPS. So you see that for a 1 megawatt UPS, you have a constraint of 20 microhenries. At 480 volts and 1 megawatt, the nominal inductance is somewhere around 600 microhenries. So our requirement is basically saying that your inductance should be below 0.03 per unit for these values. To the right, there is a picture that shows how these 20 microhenries compares to the equivalent impedance of 1 megawatt of power supplies. So these two impedances are far from each other, and that's because we need to accommodate for the additional interconnections that add to the bypass impedance. To give you an image also, here is a 2 megawatt switchboard that we were about to measure. And the measure of impedance in this 2 megawatt switchboard is usually around 6 microhenries. So that says that 1 megawatt UPS with 20 microhenries it's an easy requirement to pass. This is a simulation from a model I put together in MATLAB of our data center. And it shows that when the bypass inductance is 12 times the specification that we are given, the voltage waveform is distorted with the low frequency envelope that we described earlier, and the currents are also distorted with that low frequency component. If we reduce this inductance to 10 times our spec, then the voltages become a fixed amplitude waveform, the same as the currents. So the problem goes away. This is on the inverter impedance requirements. There are two requirements. The inverter is shown here in blue, and then there is an interconnection impedance L3 that connects it to the power supplies in the network core of the Facebook data center. The first constraint is on the magnitude, and then the magnitude of the inverter impedance should be less than the combination of a resistance and an inductance for all frequencies less than the second harmonic, where this resistance and inductance are a function of the nominal or base impedance of the data center, so that if you have more power in your data center, then this constraint may be lower. It scales depending on your nominal power. And then there is also a phase requirement on the inverter impedance, and that's the angle of that inverter impedance should stay between -85 and 85 degrees. So it must stay within that allowable region, stay away from the forbidden pink region. For the rectifier, because the rectifier is a load to the data center, the requirement in this case is for the impedance of the rectifier to be larger than a certain number. It's given as 1/2 times the nominal impedance of the system, and that's a constraint that applies for frequencies below the second harmonic. So the impedance of the rectifier should stay away from this shaded region. It could be anywhere above it. Secondly, there is a phase requirement on the rectifier input impedance, and that's for high frequencies again. We want the phase of that rectifier impedance to be in between -85 and 85. So it should stay away from that forbidden region. There is a third requirement for the rectifier, and it says that the rectifier must be stable with an equivalent inductance of 0.33 per unit connected in series with the input of the rectifier. Here is an example UPS impedance from a simulation I put together. This is just an example to illustrate some circumstances. This is the inverter impedance. So the red trace is the positive sequence impedance, and the black trace is the negative sequence impedance. So right away you see a problem, and that is that the phase goes into the forbidden region for frequencies in between the second harmonic and somewhere around the 500 hertz. So that's a problem. And then if we add to this our equivalent load impedance, we'll see that there are two intersections, one occurring at around 350 hertz, and there is another intersection somewhere around 7.4 kilohertz. At these intersections, the phase difference between the two impedances is 180 degrees, so that makes the impedance ratio be -1, and it can lead to instability. These problems could have been avoided if the inverter impedance had met the Facebook impedance specification to start with. So in this next slide, there is a simulation of the example and shows that indeed there is some resonance around a few hundred hertz, and there is some higher frequency resonance on the currents. It shows almost like ripple here. And if we adjust the inverter control to pass the spec and to obtain a different impedance that complies with that spec, by adjusting those controls, it is possible to resolve the issue and have a stable system. This slide summarizes the requirements discussed in this presentation. There are requirements to test with a series inductor for the rectifier, and there are magnitude and phase requirements for the bypass, the rectifier, and the inverter impedances. This is a call to action. Please follow the data center facility call. I'd like to acknowledge now the technical contribution of Dr. Jensen. He's a professor with Rensselaer Polytechnic Institute and a consultant for Facebook in this project. I'd also like to thank at Facebook the data center design, the strategic design and engineering, and design engineering teams. I'll be open for questions. Thank you.
Good day, everyone. This is Mauricio. I'll be ready here for any questions you may have. You can type them into the chat or the Q&A tabs that you have available. I hope everyone can tell now when your data centers may become unstable.
By the way, to get some questions, I'll just mention something that a lot of our industry partners mentioned, and it's that the instability that we showed at the beginning of the presentation, where the
Hey everyone, sorry I had some audio issues. Apparently my reception in my apartment is not very good. But I'm trying to answer the questions you put into the Q&A tab. So let me go one by one and I'll just try to type as fast as I can.
So one of the questions says, are impedance specifications typically found in our electronic component dashboards? Request from
Thank you. You will now be placed.
On the rest of the data center specifications not related to UPS. So please try to join that one as well. I tried to answer most of the questions in the Q&A tab. There are a few minutes left, so I'll stay here, but at 9:45, please switch to the other presentation.